What's up, pre-calculus students? I'm out today. It is the day before Thanksgiving break. This is what we're doing. You're watching this notes video so you understand the lesson. You then have time to do your homework. That's it for the day. That way you don't have any homework over the break. Great. We will have plenty of time to kind of practice and remind ourselves of what we're doing after the break before we take our 5.1 quiz, which we will be taking, and then jump into 5.2. Okay. And today is on function compositions. Okay. Function composition. What is a function composition? So we talked in unit 0 about how functions are machines where it's you plug something in, you get something out. Inputs and outputs. You guys are used to X's and Y's, but we saw in a lot of our tests, they don't like to say X's and Y's. They like to say inputs and outputs, Well, it's if our inputs are going to be X's, if I replace my inputs with 3, if I'm finding f of 3, I'm replacing X with 3, I can evaluate this and get an output. So 8 plus 3 is 11. G of 5. For this input, I get my output. Square root of 9 is just 3, not plus or minus 3. We can also say, hey, if this is my output, what must be the input? Again, it's a machine. You take your input, you plug it into your machine does some stuff to that input, and then you get an output. Cool? If I know my output, I know what my function is going to produce, I can try to find what the input is. Just solve an equation. Log base 2 of both sides, or you know that 2 to the 4th is 16. When does this function equal 5? I'll square both sides. Got that. Cool. Sometimes it's going to be beneficial. This is very this is very much stuff that is important to know if you're going into computer science. Understanding inputs put into a machine, output. Sometimes it's beneficial to combine multiple machines. Take one machine, boom, have it do its magic, get an output, then take that maybe potentially and do something with it. Maybe it's you have your input plugged into both of your machines. Boom, you multiply them together. Sometimes doing multiple things is a very common process when we're programming and we're trying to get results after manipulating things different ways. So we can potentially multiply, divide, add, subtract function values, our machines. F of 3 times G of 5. Well, F of 3 we found was 11. G of 5 is 3. Okay, I can do that. 33. So this is hey, multiply your machines together. F of 2 is 4 plus 3, which is 7. G of 0 is root 4, which is 2. Boom. You could divide your machines. You can subtract, you can add. I'll do the subtract, I won't do the add. 2 to the 0 is 1. 1 plus 2, 1 plus 3. 1 plus 3 is 4. G of 12 is root 16. Root 16 is 4. I get 0. Cool. And the same thing would go here. I mean, this is a good one to do because you need to remember. Oh, never mind. I thought it would be a negative power. But anyways. What I was kind of referencing earlier is sometimes we want to combine machines. Sometimes we want to take an input, plug it into our first machine. Our first machine does work. Boom. Then we're going to take that output from my first machine, plug it into my second machine. It does work. Boom. We get one output after an input goes through 2 machines. This is called function composition. It's putting one machine inside of another, but it's really doing 2 machines to one input. You start with an input, plug into a machine, you get an output. That output then gets plugged into a machine and gets a final answer. Um, this is notation for two machines. F parentheses G parentheses a number or X. What's very important is that this looks like multiplication. It is not. This is not the same as F of 12, say, times G of 12. Not correct, okay? This is F of G of 12. Essentially, it's saying you will take 12, plug it into G. You will get an output. You will take that output, plug it into F, and boom, after putting 12 into both machines, not really put 12 into both machines, after 12 goes into G, outputs, that goes into F, boom, we get one answer. Okay? Show you what it looks like, and it kind of makes sense mathematically if you just kind of think about PEMDAS, order of operations. We like to work like inside out with parentheses. If I gave you like something like this, parentheses 1 plus 2 plus 3, parentheses squared, what would you do first? I'd probably work on the innermost parentheses, the 1 plus 2. I'd add those two together, then I'd add 3, then I'd square everything. So this is kind of the idea. We can find G of 12. G of 12 is root 16, which is 4. Great. G of 12 is 4. I'm going to replace G of 12 with what it's equal to. It's equal to 4. Now it becomes F of 4. Well, F of 4 is 2 to the 4th plus 3. That's 19. This is my answer. This is my number 12 plugged into G. G outputted 4. 4 then got plugged into F, and we got the output of 19. We take the number, kind of let the machines do their work. We get our answer. This is function composition. So anything can go in any order. Here we can have F, G of F of 1, and this is how it's read. It's read G of F of 1. It's not G F times G times 12. It's G of F of 1. So we can find F of 1. F of 1 is 5. We can find G of F of 1. F of 1 is 5. G of F of 1 is G of 5. G of 5 is the square root of 9. The square root of 9 is 3. So we took it 1, we plugged it into F. It got me an output. That got plugged into G. Boom, it got me my final answer. All right. We could also compose our expressions of x's. This is very common. If you're going to be doing this over and over and over again, say I wanted to find F of G of 12, of 9, of 5, of 6. Maybe I want a program, be able to plug into my program and have it do repeatedly. Well, like we can compose our functions so that instead of doing one machine output, another machine output, it's just like, boom, push the machines together, make it one larger machine, plug it in, get the answer that we're looking for. So for example, we have F of G of X. What would that look like? Well, I know what G of X is equal to. It's equal to root X plus 4. I can replace G of X with what it's equal to. Now, this is where things get a little tricky. F of X is equal to 2 to the X plus 3. Well, I don't have F of X, I have F of G of X, I have F of root X plus 4. Well, wherever I see X, I'm replacing it with root X plus 4. What does that look like? Well, 2 to the root X plus 4 plus 3. This is my bigger combination of machines. Now, like we can go back to this question, 12, and plug it into this machine, and we got square root of 12 plus 4 is the square root of 16, which is 4, 2 to the 4th, 2, 4, 8, 16, plus 3, 19, boom. Like we've combined our machines, we've made it a larger machine versus treating it as two separate machines. We can honestly just like say, plug in 12 into F of G of X, and boom, you get 19. Isn't that cool? So let's do that with g of f of x. So f of x is 2 to the x plus 3. So g of x is root x plus 4. Instead of x, I want to have g of 2x plus 3. Wherever I see x, I'm replacing it with 2x plus 3. What does that look like? Root 2 to the x plus 3 plus 4. And if you want to, you can simplify. We get root 2 to the x plus 7. This is now like a bigger machine. G of f of x is root 2 to the x plus 7. Let's see how that works. Let's do g of f of 1. If I plugged in 1 into this larger machine, I got 2 to the 1 plus 7, which is 9. Square root of 9 is 3. I get the same answer here as if I took the two machines separately. Here, I'm taking 1. I'm plugging it into the large machine g of f of x, and boom, I get the answer that I was looking for, 3. Okay? Sometimes you can put a machine inside itself. Let me rewrite f and g because we're going to be using it. Cool. So f of 1. And again, with numbers, if you're just doing a couple of them, it might be beneficial to just treat them as two different machines, two different functions. Finding f of 1 is 5. Finding f of 1 would be f of 5. F of 5 is 2 to the 5th, which is 32, plus 3, which is 35. Okay, cool. Let's get that answer a different way by combining my machines. F of x is 2 to the x plus 3, so I'm going to replace f of x with 2 to the x plus 3. Now, I will replace x with 2 to the x plus 3. Instead of f of x, I want f of 2 to the x plus 3. Wherever I see x, I'll replace it with 2 to the x plus 3. What does that look like? Don't be afraid. It'd be 2 to the x plus 3 plus 3. Now, this is a larger machine. Let's see if it works. Let's plug in 1, 2 to the 5 plus 3. Okay, good. Yeah, so it's like instead of going one then the other, we create a larger machine. G of 12. G of 12 is 4. We've done that. Then we do G of 4, which is root 8. Probably need to remember how to simplify this to be 2 root 2. What would that look like as a larger machine? Well, G of x is root x plus 4. G of x means wherever I see x, I will replace it with root x plus 4. I think if there's anything you guys probably need to like work on, it's this part of it. This would be the larger machine G inside of G of x. If I plugged in 12, I got the square root of 16 plus 4. It's the square root. It's 4 plus 4, which is 8. I'm going to get the same answer, 2 root 2. Okay. Heads up, in other math textbooks, you might see this notation with a circle. You're typically used to seeing like circles or dots as multiplication. Well, dots are multiplication. Circles mean composition. Could also be read f of g of x. On the AP test, we've only seen the notation once, but the notation was like, hey, f of g of x is equivalent to f of g of x. Like most of the notation we see on all of your problems are this notation versus the other composition with circle notation. Okay, bunch of different examples. I want us to just do a couple of them. Actually, I'll do them all. Maybe you're going to do them right now and see if you can get the right answers. If you're getting the right answers, boom, like move on. You can skip ahead. If you're not understanding things, then go back. Probably let's make sure we can get the composition of expressions correctly. because I know you're going to make mistakes on those. So, like, let's get these answers quickly, but then you're going to make mistakes here. I promise you. Like, if I was in class, I would like really look forward to doing a couple of these problems so I could catch many of you making very simple mathematical mistakes. So here we go. B of 4, log base 2 of 4 minus 5. This is 2. That's the exponent. 2 minus 5 is negative 3. So this is a of negative 3. A of negative 3 is 9. This is 8. D of 9 is 1. Square root of 1 is 1. C of 1 is 4. B of 1 is 0 minus 5 is negative 5. C of negative 5 is negative 5 plus 3, which is negative 2. Negative 2 over negative 5 is 2/5. B of a half is negative 1. 2 to the negative first is a half. If you're not sure what that is, you got to rewrite it as an exponent. Negative 1 minus 5 is negative 6. A of negative 6 is 35. We can compose 3 things. This is 3 different machines. Boom. D. We're going to take 24. Get it in D. Get an answer. Plug it into B. Get another answer. Plug that into C. Let's see what that looks like. D of 24. What's 24 minus 8? 16? Yeah, we really like 16. It's 4. Okay, boom. Our first machine worked. I took 24. I plugged it into D. D got me 4. I will take 4 and plug it into B. I got 2 minus 5, which is negative 3. I will take negative 3 and plug it into C. Oh, 0. Nice. A of 1 is 0. D of 0 is negative. Ooh, this is good. The last one, A of 1 is 0. D of 0 is root negative 8, which is like 2 root 2i, or which is like undefined imaginary. We're going to talk about like, sometimes when you compose things, we got to pay attention to the domain. We'll do that later. Let's compose some expressions using x's. Let me see which ones I think you're going to mess up. A of c of x, I bet you mess up on. A of e of x, I bet you mess up on. Prove me wrong. Okay. What's a of c of x? C of x is x plus 3 over x. So I want a of x plus 3 over x. Not 3. Okay. X squared minus 1 is a. Instead of x being x squared minus 1, it's this. This is going to replace x. So I get quantity x plus 3 over x being squared minus 1. This is a problem you're going to see on your test. This will not be an answer. You might think this is an answer, but you need to simplify. Many of you will be like, okay, I got this. X squared plus 9 over x squared minus 1, and you are wrong. And this is what I wanted you to check on. Now, when you square x plus 3 over x, it's x plus 3 over x times x plus 3 over x. You need to multiply x plus 3 by x plus 3. It's x squared plus 6x plus 9. If you didn't make that mistake, good, but I bet you some of you did. Now you might want to think, okay, this is my answer. No, you probably won't see that answer. Let's remember rational functions, combining things. The answer you would probably see, your simplified composition would be 6x plus 9 over x squared. This is what we would expect you to get. Cool. Let's do a of e of x. A is x squared minus 1. E of x is 3x minus 2. Okay, so it's a of 3x minus 2. Wherever I see x, I'll replace it with 3x minus 2. So it's 3x minus 2 squared minus 1. That's a of e of x. You will not see this as an answer. You'll be responsible for simplifying. Don't you dare tell me 3x minus 2 squared is 9x squared minus 4. It's 9x squared minus 6x. If you need to write it out, write it out. Minus 12x plus 4 minus 1. And then I'd get 9x squared minus 12x plus 3. Okay? This would be what we'd look for after composing our functions. This is the stuff you probably need to practice a little bit more than using numbers. A of x plugged into c of x. C of x is x plus 3 over x. A of x is that. So wherever I see x, I will replace it with x squared minus 1, giving me x squared minus 1 plus 3 over x squared minus 1. This becomes x squared plus 2 over x squared minus 1. You could factor if you wanted to, but you can't factor the top, so we're good with this. C of d of x. D of x is root x minus 8. C of x is x plus 3 over x. Okay. Taking d of x, plugging into c of x. This is c of root x minus 8. I will plug in root x minus 8 wherever I see x. This becomes root x minus 8 plus 3 over root x minus 8. Cool. Having a composed expression with variables like we just did here is very beneficial. If you need to find c of a of 2 and c of a of 3 and c of a of 4, if you can plug in any value, like this is something where it's like, oh, I need to program something so I can take one, boom, do this quickly, get the output. Having composed expressions with variables beneficial, okay? When you're like writing a program, but heads up, it's also helpful to pay attention to the domain so that like you have your composition, your mashing of two machines. Make sure we can only plug in certain values into that machine or your program's going to break. Okay? Domain is the idea. Like, what are the values that you can plug into your big machine for it to work? Make sure we don't plug in bad machines or your program's going to break and you got to go debug it. Okay? So, domain, making sure like if somebody on their keyboard accidentally types in 2, before you enter it into the program, your machine, your like program is going to be like, you're not allowed to plug in 2. 2's not in the domain. It's going to break my code. We don't want to do that. That's the idea behind like paying attention to domain. So what are some of the domains that we have to worry about? Let's look at like a of c of x, which is simplified 6x plus 9 over x squared. If we have an expression for it with x's, we can just look at it and be like, yo, don't plug in 0. If you plug in 0, you're going to be dividing by 0. My program's going to break. My machine's going to break. That's going to be bad. So like this is something that could be programmed in first. It's like, here you go. If anybody types in 0 and tries to plug it into my program, stop them and say you're not allowed to do that. What's another good one? This one's all good. Oh, c of a of x, which is x squared plus 2 over x squared minus 1. Now, again, this is helpful if things are put together. You can kind of pay attention to like, oh, yeah, for this composed program, don't plug in 1 or -1 or things are going to break, okay? You compose the functions. You can pay attention to the values that you can't plug in. Then let's look at C of d of x, which is root x minus 8 plus 3 over root x minus 8. Now, we know that we like to only plug in positive values or values that are equal to 0 into the square root. That's something that's important. Square roots like to have zeros or positives. Remember, logarithms like to just have positives. You can't plug in 0. So in this one, it's like, okay, well, if I'm paying attention to the square root, x minus 8 has to be bigger than or equal to 0. Well, that means x has to be bigger than or equal to 8. Okay, that's a good restriction. But we also remember that we're not allowed to divide by 0. If x was 8, we'd have the division of 0 in the denominator. We are going to say, well, we actually can't have 8. Hey, for this program, make sure you are only allowing people to plug in values bigger than 8 into it, or we're going to get an error. Or we're going to get like an imaginary number. Let's just pretend imaginary numbers are errors right now. Okay, so paying attention to domain is important. You'll see next class, we're going to talk about inverses, that paying attention to domains and ranges are important. This one will just keep it simple and just be like, don't worry about like, there are ways to think about this where like you understand your domain of your inside function. You understand what the range is of your inside function. You make sure you restrict that range, which means you restrict the domain so that you can plug it into the set. It's like that's confusing. Compose the functions, you'll be able to see what can't be plugged into your big machine. All right. The rest are just like different representations of machines and how you can compose them and have them work with each other without having an expression, like without having equations. For example, like here is a g function for certain x values. Here's an x function. So tell me if you plugged in these x's, -3, 0, 2, 5, and 9, into the big machine of g inside of f, what do you get? All right, well, I plug in -3 into g, I get 2. I plug in the x value 2 into f, and I get -5. Boom. That's f of g of -3. -3 went to 2. I plug 2 into the function f. F of 2 outputs 5, -5. Okay. G of 0 is 5. F of 5 is -1. Got it? You can do the rest. I'll do them really quickly. Cool. Remember, we can compose functions inside themselves. What would g of 0 be? Well, if I plug in 0 into g, you grabbing your quiz? Yep. G of 0 is 5. Okay, cool. G of 5 is 1. G of 0, 1. F of 1. Okay, f of 1, if I plug in 1 in for x, my output's 2. F of 2, if I have my output of 2, 2, input of 2, my output's -5. You grabbing your quiz? What do you want?
The practice problems were really hard.
Yeah.
If we like don't.
What do I always say?
I know I get the quizzes.
Then you're going to be fine. We make the quizzes off of the test.
I feel like
we don't make the quizzes. We don't make the practice problems off the test. The practice problems we find later. Sure. I don't think you're going to be tripped up by wording because if there were really tricky wording problems, now there are some like, input output kind of questions where you understand like exponential functions, if the input increases by one, the output's going to increase by a multiplier. Logarithmic functions, it flip flops. The input has to like increase by a multiplier for the output to increase by one. We understand that like powers of your input produce like one small step change of your output. Go with that. Like you'll see a couple of those,
Like
but
the charts.
those are the charts. Yeah, you're gonna have a couple charts, but it's the quizzes. If you guys are okay with your quizzes, I think you'll be okay with the test. All right.
Can we take our quiz, our Unit 6 quiz?
Yes.
Or,
Do you happen to have an extra copy of like the other quiz, like the Unit 6 quiz, like the other copy that I have?
It's online. I threw them all out.
Okay.
Okay.
Yeah, because last night I wasn't there, so.
Yeah, you should have emailed me. I would have posted it, but I posted it this morning.
Okay, thank you.
Okay. All right, cool. We can see functions on graphs. Like here's a g function. Here's an f function. We're going to challenge you here. We're going to make it a little bit harder. We are going to be asking you to find some f values or g values that are not obvious. For example, what's f of negative 2? Okay, and then we're going to compose it. F of negative 2, so here is 0, this would be negative 1, this would be negative 2. What is that y value? Now, I have to show you this because like I get questions every year in my AP calculus class. Students like, how the heck do you get that? It's like, we should be able to figure it out. Now, it might not be like, and it's an easy way to figure it out. You don't have to do the complicated way of like, oh, what is this equation? You don't need it, okay? What is f of negative 2? That's the question. Well, I can see this y value here is 1, 2, 3, 4, negative 4. I can see this y value here is negative 2. All right, cool. So I can see this y value here is negative 3. What's my slope of this line segment? Up 1 over 3. Right there, that slope is up 1 over 3. Remember when we talked about rates of change? Up 1 over 3 is the same as up a third over 1. This is the ticket, guys. What is f of negative 2? Well, I start at negative 4. I go up a third over 1. I'm at negative 3 and 2/3. I go up a third over 1. I'm at negative 3 and a third. That's negative 7/3. We're expecting you to be able to get that value by applying a slope one x value at a time. Okay? Let's do that again. The slope of this line segment is 1/3. What is the value here at negative 2? Well, I start at negative 4. I go up a third over 1. I'm at negative 3 and 2/3. I go up a third over 1. I'm at negative 3 and a third. That's not negative 7/3. Negative 3 is negative 9/3. Negative 3 and a third is negative 10/3. My bad. I was thinking 2 and a third. Cool. Let's look at g of negative 1. Here's g of negative 1 right there. I'm trying to find what is that exact value. Okay. This is just a quick little like, how can we challenge you within this unit? This is one way. Okay, I got this y coordinate, which is 1, 2, 3, 4, 5, 6. I got this y coordinate here, which is 1, 2, 3. I go down 1, 2, 3 over 1, 2, 3, 4. The slope of that line segment is negative 3/4. Down 3 over 4. Go back to rates of change. Make sure you understand a slope is a rate of change. I'm going down 3/4 of a y per x. I start at 6, go down 3/4, I'm at 5 1/4. Go down 3/4, I'm at 4 1/2. Go down 3/4, I'm at 3 3/4. So 3.75 or 3 3/4 is 15 quarters. Got that? Or, conversely, start at 3. I'm going to have to go up as I go left 1. This is probably easier to do. Up 3/4 over 1, 3 3/4. Cool? All right. So, boom. Couple challenges here. Some answers that are not whole numbers, and you need to be okay with it. We see it in AP Calculus, and I want you to see it now. Okay? So, hopefully, you remember it next year. F of G of 3. Okay. We're going to plug in the input of 3 into G. G outputs 1. This becomes F of 1. F of 1 is that value. We've said this line segment slope was 1/3. So I got -2 here. I'm going to go down 1/3 over 1. So this is -2 1/3. This is -7/3. G of F of -1. F of -1 is -1, 2, 3. -3. G of -3. -1 to -3. Is that Y value there? Remember the slope of this line segment was down 3/4. So go down 3/4, down 0.75. You got 5.25. I'll accept that, or I'll accept you guys doing 5 1/4. So that's 21/4. All right, challenges for the rest of them, and you'll do your homework and you'll see more of these. F of 4, 1, 2, 3, 4. F of 4 is that y coordinate 6. G of 6, 1, 2, 3, 4, 5, 6. G of 6 is that value. What is this slope? This slope is up 1 over 2, which is the same as up 1/2 over 1. I'm at -1, 2, 3, 4, -4. This is going to be -3.5. F of 2 is -2. G of -2, we found. No, we didn't. So it's 3 3/4. It's 4.5. Great. And I'm going to skip that one. And then the last one is just combining a table with a function. It shouldn't be that big of a deal. And we can also combine it with graphs. Like, be ready to combine anything and be able to deal with it. If I said, what's J of H of -2? It's like, all right, well, here's H. H of -2 is 2. J of 2 is 3 squared, which is 9. Great. What about J of F of 2? Oh, F of 2 from over here is -2. That would become J of -2, which would become 3 to the -2, which would be 1/9. Combining these things should not be crazy. We can have a table, an expression, a graph, understanding, and I probably would have gone back if I wasn't rushing, like making sure you understand like what the values are, F function values. Like what's G of 3? Okay, well, when the X value is 3, what is the Y value? Essentially, what's the output? That's what a graph is, just like for your inputs, what are your outputs with your machine? So be ready for tables, expressions, graphs, composing with X's, and that's it. Nothing super crazy for this lesson. It is stuff that you've seen before. So I'm going to do the homework video at some point, probably during lunch, and hope you understood this lesson. I'm sure many of you are just working on your homework so you can be done. The sub is in charge of making sure you finish your homework before you do whatever you want to do. All right? I'll see you guys after the break. Happy Thanksgiving. Later.